Hello, you wonderful digital denizens of the earth, of the planet. Welcome to another calculus lecture. This one's about implicit differentiation. Again, these lectures are based on the OpenStax Calculus Volume 1 textbook. It's a free resource. It's an awesome resource. I would highly recommend you go check it out. If you need proofs, if you need more examples to work, if you need more problems, if you need more clarification, they have some interactive modalities too. So I would highly recommend that you check this out. All right, implicit differentiation. We know what differentiation is. We've been doing that a lot because this is calculus class. But what does implicit mean, right? First off, I want to talk that, you as a calculus student, at this rate, you probably know that there's a lot of different types of functions. You've been learning about functions. You've been working with functions. You've been doing a lot of stuff with functions. This goes back into very early math. We're used to a function of the form y equals ax to the n, and this is a function. Y is a function of x, right? So we have this is a normal function, or not a normal function, but type of function that we're used to, but functions don't always look like that. So it's important to remember everything is not as it seems, right? So we have two different types of functions here. We have explicit functions and implicit functions. The things that we are used to and we work with a lot are explicit functions. So we express y explicitly in terms of x. So we have our y alone on one side of our equation, and we have our x's and everything else over here. Then we have an implicit function, right? So this is where the relationship between the function y and the variable x is not expressed by an equation where is expressed by an equation where y is not expressed wholly in terms of x. So we have something like this: y minus x squared equals 1. This isn't usually what we do because, again, like this y is another word for f of x. So this here is f of x minus x squared equals 1. So that gets tricky because that's not usually how we like it. Our calculators don't take it like that very much. The thing is, we can still differentiate these implicit functions. We can do implicit differentiation. We can find the average rate of change because these are things that we can graph, right? So this is not a function as we know it. This is a function as we know it. This is a function as we know it, and so is this, because it passes our vertical line test. So if you come over here and you draw vertical lines, they only hit the graph once, right? These work, right? But vertical line test, it hits here and here with the same vertical line, right? So it's not technically a function as we know it, but this is graphed. There is an instantaneous rate of change here, so there is a way to find dy dx here, right? So how do we go about it, right? So we have a strategy to implicit differentiation. So to implicitly differentiate an equation that defines a function y in terms of a variable x, we must take the derivatives of both sides of our equation. So we have to remember that y is a function of x, and so we can't forget chain rule, right? So when we take the derivative with respect to x as a function of x, right, we're given just f prime of x, the derivative of f of x. But when we take the derivative with respect to x of something in terms of y, right, we have to take its derivative and then multiply it by the derivative of the inside. So we have this chain rule here because this is our function f is in terms of our function y, right? So we have to multiply by the derivative of the inside. So then we'll get all of our terms of dy dx alone on one side, and then suck all of those out to one part, and then we'll usually have we'll have something of the form dy dx times the quantity of is equal to the and then we end up dividing, have dy dx equal to our this over our this, right? It works out pretty well because here we're left with this dy dx, and we have found what the instantaneous rate of change is, which is very cool. So now we have an example, right? We assume that y is defined implicitly by this equation. Then we'll find dy dx. And so now I'll take this to the real world where I'll work it out by hand so you can see some of my tricks, some of my best practices. So I'll see you in the real world, and I'll see you when you get back.
Alrighty, this is our first implicit differentiation problem. So
we're assuming that y is defined implicitly in the equation, right? So we want to find dy dx. We're taking the derivative with respect to x. So what we end up doing, this splits across, our sum rule, right? So we'll end up having d dx of x squared plus d dx of y squared is equal to d dx of 25. This is our constant rule, right? So this just ends up being 0. Here, we have, we're differentiating with respect to x. We have an x, so that's easy enough. We'll have 2x with our power rule. And then here we do power rule again, take the derivative just as normal, but we have to, this is y is a function, right? So we need to do chain rule. So we need to multiply by the derivative of the inside, which is dy dx. So now what we'll do is we'll get things, we'll get every dy dx term alone. So we'll have 2y dy dx, and that will be equal to negative 2x because we'll subtract 2x from both sides. And now we'll divide both sides by 2y. So these will cancel, and we'll have dy dx equal to, these 2's will also cancel. This will be negative x over y. And this is our answer. All right, we're back. We'll move on to another equation. So we're assuming that y is defined implicitly by this equation, and then so we want to find dy dx. So we're gonna do our example in the real world, and then I'll see you once we get back. All right, here's our second implicit differentiation problem. We're assuming that y is implicitly defined by the equation, and we're tasked with finding dy dx. So here, if we want to find, so we'll end up start by taking the derivative, right? So we'll split it across addition, because we know we can do that. So we'll end up having d dx x cubed sine y plus d dx of y is equal to d dx of 4x plus d dx of 3. So get these easy ones out of the way first. This is our constant rule, so this will go to 0. This is our power rule, so this will turn into just the number 4. Here, this one's pretty easy because this one ends up just being dy dx, because power rule makes it 1y to the 0, which is just 1 time, but we have to multiply by the derivative of the inside, so this ends up being just a dy dx. And then over here, we have to do a product rule, right? So our f of x here is equal to x to the third, our g of x is equal to sine of y. If we want to do f prime of x, this is equal to 3x squared, and then g prime of x is going to be equal to cosine y dy dx. So we'll have x cubed cosine y dy dx plus 3x squared sine of y. So we have that plus a dy dx. It'll all equal to 4. Now we want to get our dy dx terms on the same side and our non-dy dx terms on the same side. And notice that it's not just like the y terms, it's the dy dx terms. So we can have a y term over here. So this we'll end up rewriting this as x cubed cosine y dy dx plus dy dx is equal to 4 minus 3x squared sine y. So now we'll distribute
a dy dx out to the front. So this will end up being dy dx x cubed cosine y plus 1 is equal to 4 minus 3x squared sine of y. Yes, sine of y. And then we'll end up dividing both sides by x cubed cosine y. I guess I'll put my brackets here. X cubed cosine y plus 1. And so these will cancel. So then we'll have dy dx is equal to 4 minus 3x squared sine of y all over x cubed cosine y plus 1. Now, if we wanted to find the slope at a point on the equation, we could plug in a y and an x, and then that would give us our slope, because that's what our derivative is. So we've successfully implicitly differentiated this equation.
All right, we're back. And we have one last example. We're going to find the second derivative of what we found in our first problem. And so we'll chop away at this. It works the same, but a little different. If I don't remember to, in the real world, I just want to say, everyone, please like, subscribe, comment, press all the buttons. I want you to press as many buttons as possible. If you didn't like the video, you can dislike the video. If I did something wrong, let me know. I hope I didn't, but I know that nerds love to nerd snipe, and every one of us is mortal. Thank you for taking the time out of your day to learn some calculus, make yourself a better person. I love calculus. You should love calculus too. Unfortunately, calculus feels indifferent about us and really just wants something more platonic. But that's besides the point. We're going to work this last example, and if I don't tell you to have a great day then, have a great day.
All right, so last example, this equation might look familiar. It might look familiar because we did this equation before. But here, we are being asked to find the second derivative. So here, the second derivative. This is what we want to know. And we already know the first derivative. We already know that dy dx is equal to negative x over y. Right? And we know that the second derivative is the derivative of the first derivative. So we're going to implicitly differentiate this again. So if we take the derivative of both sides, so I'll draw my brackets. This will just end up being the second derivative. So d squared y over dx squared equal to, now we can do quotient rule or product rule here, because we can play with location and then do some other things, but I think we're going to do a quotient rule. So we have our time-old honored tradition of low d high minus high d low over low low. So our top will be f of x, and our bottom will be g of x. And one other thing we have here is that this negative is a negative 1, so this ends up being negative d dx of x over y, which also makes this easier. So if f of x is equal to x and g of x is equal to y, then f prime of x is equal to 1, and g prime of x is equal to dy dx. So we'll then have negative our bottom, y, times the derivative of our top, which is 1, minus our top, x, times the derivative of the bottom, which is dy dx, all over, I'll put a little parentheses there so we don't get tripped up with our negative. This will be all over the bottom squared, and the bottom squared is just y squared. But we're not done yet, so we already know we can solve for this, right? But that's not really what we want to know. We want to know the second derivative, right? We already know this. We've already discovered it, so we can just plug and chug. So we can have this equal to the negative of y minus x times negative x over y, all over y squared. And so this distributes in. So we have, again with our parentheses, we have negative y plus x squared over y squared. And then we'll distribute in our negative, and we'll end up getting that negative y minus x squared y all over y squared. And then this is the answer to what our second derivative is. So this is our d squared y dx squared. Congratulations! This is our last example for implicit differentiation. I hope this elucidated you, helped you increase your understanding of implicit differentiation. You know, I probably already wished you a good time on the PowerPoint, but I'll wish you a good time again. Go forth, be plentiful, do great things, do great math. Click all the buttons down below. Like, comment, subscribe. If you have any questions about implicit differentiation, be sure to shoot me an email or check the OpenStax textbook. Thank you very much for your time today and paying attention to my little example. I've been Liam Neidig,